Hello again, this is Michael Hicks, your professor for Econ 602. What we'll be doing today is walking through, in a rather short video, how to use Excel for the statistical work that you'll be doing here. And so what I've done here is to your right, I have open a spreadsheet, which I will post also to the Canvas site, which you can use at home to do some experimentation on your own. And what I have here is data from each U.S. state in 2010. This is the um, uh, personal income, per capita income in each state in 2010, and then in 2019, right? And this is total personal income in millions. This is per capita income for each of those locations. And then what I have is the bachelor's degree and the advanced degree share in each county. So I'll just do a couple of things here with the spreadsheet to make this easier. I'm going to hide things that I don't wish to look at, just to unclutter my spreadsheet. And the first thing I wish to do is to add what's known as the analysis pack. So I go to File, Options, Add-ins. So that's File, Options, Add-ins. Then I click on Analysis Tool Pack. And in most circumstances, you just double click this, but here it's a bit buggy. You got to go to Manage the Excel add-ins and click that Go. And you can check this add-in available. You all should have this analysis tool pack on yours. Most all do. There are the analysis tool pack for Visual Basic allows export to other software. The solver can do some things, particularly in ops research, that you might find useful. And you just click OK and you get that. And it appears on the data screen over to the far right. And there's data analysis here. And this will be the series of statistical functions that we'll talk about through this class and in the guest lectures. All right, so let me just walk through that again. File, Options, Add-ins, Analysis Tool Pack, Manage Excel, then Analysis Tool Pack. And that will give you the statistical tools. Many of you have asked about whether I need a plotting or graphing calculator and the like, but this will give you everything that we'll need to do in the context of this course. And it will be a good supplement to what you work with later on. Excel is sort of the industry standard. So if you haven't been in business, you may not have used a lot of Excel, but this is going to be something necessary for your data management. The step above Excel is to work with data in a very large programming data like base language like SAS or R. And we'll not be working with that in this class, so you may get into that in other parts of your MBA. And so what you've learned so far is, summary statistics and the meaning of each one of the steps. A mean, a variance, which is the standard deviation squared. The mean tells you the central tendency measure. The variance or standard deviation tells you, the spread of that. The skewness, right, which is really the mean cubed, tells us the symmetry or asymmetry of the distribution around the mean point. And then the kurtosis, which is the fourth moment, tells us a little bit about the tailedness, how far or how thick the tails of the distribution of the statistics are. And so the video that you just saw on the central limit theorem tells you, or excuse me, the central limit theorem video that you'll either have watched or about to watch will talk about the importance of sampling distribution. There's two sort of concepts you have to think about. Either we're working on a population, in this case it's a population, it's the US states and District of Columbia. So there are 51 observations here. The other option that we often deal with, particularly in business and marketing, is sampling distribution. So we're going to be drawing a sample either through a survey, or we're going to pull out a subset of observations using a random number generator to find out something about the population. And we like working with normal distributions because it eases the analytical challenge that we do. And the central limit theorem tells us when we draw sampling character, we draw random samples from a population, regardless of the population distribution. Those random samples will appear like a normal distribution when they hit some size. And there are several different central limit theorems. The most common one, the one you learn in middle school or high school, is roughly 30, that about 30 observations or a sample of 30 out of any population is sort of the minimum for any inferential statistics. Fact is that that was a big problem in statistics from, say, the early 1900s, when the t-statistics was devised for quality control all the way up through the 1980s, let's say. But the mass availability of computers means that we can do huge statistical functions using computing power that was unavailable to even many scientists up until the 70s or 80s. And so it's less of a problem. We're more likely to be working on large sample sizes where we don't really have to worry about the central limit theorem. Where you will have to worry about it is if you're doing sample distributions in a public opinion poll or a marketing survey or something like that. And again, think about the way to think about this is really straightforward. Let's suppose that you were to have a large auditorium full of people. And then as people left the auditorium, they were randomly left the auditorium. And your goal, as you observe them to leave, you notice characteristics. Were they, let's say, African American or white? Were they male or female? The larger, and what you were trying to deduce was, what is the distribution of people who were inside that auditorium? What is the statistical characteristics? What share are African American? What share are women, for example? And so the more observations that you get out of that sample, let's say it's a UT Stadium, University of Tennessee, there's almost 100,000 people there. You're watching the exit door and people are leaving randomly one at a time. Well, the first person leaves, and it doesn't matter who it is, you're not going to be very trusting that that is a representative sample of the people inside the stadium. So if one person leaves, it doesn't matter really what you observe, that it's not going to be very representative. And let's just say we have two populations here represented nationally, so roughly 49.5% men, 50.5% women, which is roughly the national share. And let's say we have 14% African American, and the rest are non-African American. And so probabilistically, the first person to leave would be a white woman. So if you were to observe that and observe on one, if you made that inference about what the distribution was, you wouldn't know anything really useful. And let's say then 2, 3, 4, 5, 6, 10 people left, just randomly out of here. Out of that, you'd expect roughly 5 men and 5 women, and you'd expect roughly 1 to 2 African Americans and the rest non-African Americans leaving. That's sort of the national distribution. But even with 10, you wouldn't be, one person off could really bias this. So if there was randomly one more woman, you'd say 60-40 or the opposite. It would not give you a very clear picture of what was going on. So statisticians normally think you've got this random draw of people walking out of the stadium. If you were trying to deduce what the population shares of those characteristics were inside the stadium, sort of 30 is the minimal number that you would have to give you any sort of inference. More likely, you would want to have 300 or 400 or 600 or 800 to really give you a good sense of who is in there. And we're in this class in the electoral season. And so what's happening now is you're getting a lot of surveys of voter preferences for the GOP or Democratic candidate, and they're reporting 300 samples. So they're calling 300 people. That's sort of the enough that would give them statistical confidence that they have sampled across the domains of interest, which are a lot more than just gender and race. That I have just given you, it would be across income categories. And so the central limit theorem goes up the more categories you have. And so as you watch polls, and since you're taking a statistics class, that'd be a wise idea. As you watch polls over the next several weeks, observe that they get higher sample sizes, they get closer to the elections. So in places like California, where it's very skewed towards Vice President Biden, they're going to keep sampling 300 people in California because that's going to be representative of the mean. In a battleground state such as excuse me, Michigan or Wisconsin or Ohio or Florida, they'll be surveying like 600. So that's just an interesting way to think about what's happening with these distributions. And so what I want to do here is sort of get a picture of what's happening. So I'm going to go to insert, and I'm going to go to this graphic, which is a statistics chart. And there's several other in here, but I'm going to start with the histogram. Excuse me. And I'm just going to begin by selecting data on per capita income in the state. And I'm going to click go. And that's going to give me a distribution of 5 different bins, or called, right? And so you can see that there are 5, there's 50 states, so there's 10 states. There's really 51 here. There's 10 states that fall between 48,468 and $57,568 income. And then there's the lowest is in the 39,000 to 48 category, and then there's some that are a lot higher. And what I can do here is format the axis, and that allows me to change the number of bins. So let's say I wanted to see 10 different bins in this histogram. That gives me a picture of what the distribution would look like. And so that would give me a good snapshot of what the distribution looks like. If I were to draw a graphic, you could see it has a mean, somewhere in this category. I'll show you how to do that in a minute. But the median is going to be to the left of that because they're skewed to the right. So it's going to have both skewness and kurtosis measures that indicate a skewness to the right and a kurtosis, or thickness and length of a tail. And so this is a way to visually depict this statistic. So now let's go to data analysis. And let's see if we can look what in this case, the descriptive statistics look like. So we'll pick a input range, which is the exact same range that we just had, right? And we want for the output range, I want it to go right here. Oh, I had to pick the summary statistics, excuse me, though. That gives us this data. So let's look at the important things. So the mean here is in this bin between 52,000 and 5,700. So the mean this is the most common measure of average. And you can see that mean is to the right of the median. The median, right, is at 52,937. So it's in this, so it's the same category, but it's to the left of the mean. And so when the mean and the median have a different point, they tell you if there is skewness around this. So we would also this is the sample variance, right, which is very large. And we can, just to see how large it is, we'll give it a 93 million. And let's just test if that standard deviation is the if the sample variance is the square of the standard deviation. So we'll just test to see if their calculation's right. This is the squared value, and boom, it's exactly the same thing, right? And then you can see kurtosis and skewness are both skewed to the right here. There's a range of $45,000 between the poorest per capita income and the highest, which is Washington, D.C. The minimum is $39,000 and the highest is that Washington, D.C. District of Columbia, $84,538. And so that gives you the first sense of data about what we would want to observe about distribution. Now let's do one more before this video gets too big. Let's choose a different set of data. Let's look at the distribution of the share of bachelor's degrees in each state. Wow, right? So, and let me go to adjusting the axis here. I want, in this case, the number of bins to be 10. Right. And so what you can see here is that you have sort of a close to a normal distribution, except for this outlier, which happens to be Washington, D.C., which is why so many folks don't like doing a state that's wholly urban. There's only really one state that's wholly urban, although both Connecticut and Delaware are getting close to it. And you can see here there are some of the characteristics of a normal distribution here. Now let's go to the same data and we'll do some analysis, data analysis. I want to do descriptive statistics. So I'm going to pick that bachelor's degree. I choose the same output range and let's hit go. I'm going to overwrite the data, right? And that gives us, again, the mean is at 30.63%. Standard, or the median is 0.299, so it's the median is less, so it's skewed to the right. If the mean's to the right of the median, it's skewed. And then we have this sample variance, and we retain that square of the standard deviation, which is the same. And then kurtosis and skewness are both positive, so it's skewed and shifted to the right. A normal distribution would normally be centered. We don't worry about on zero. We don't normally worry about that. We could always recenter the data. We could divide each one of them by the mean, and that would give us a normal distribution with a mean 0 and some common standard deviation, but we're less worried about that. And so the first thing you need to do, I would suggest, is open this spreadsheet, download it from the class module, and load data analysis into your spreadsheet, and do the same sorts of things so that you're comfortable looking at these histograms. And what we'll do in the next episode is I'll show you how to begin thinking about a hypothesis test. Thank you.